talk about the unification of probability and logic for learning. And as one of the reviewers has pointed out, this work is refreshingly impractical. So, so be warned. It's dealing with a deep, old problem: how to properly combine logic and logic and probability, and in particular, and that is what essentially all systems get wrong, so that it then also works for learning and induction, and this particular universal hypothesis. Okay, and we worked quite along on that all together here with my co-authors to get that right, in the sense that we have a formal system now, but it is refreshingly impractical. Okay, so let me first give you, well, the motivation is clear. If we want automated reasoning systems, they have to deal with uncertain knowledge, and this has many applications. I don't have to list them. And the difficulty is, having a completely satisfactory solution. And if you have sort of a limited solution, there will be some problems where it fails, and though it's not general anymore. And we just, in a sense, address this problem head on. So the classical philosophical problem is the black ravens problem. So consider a sequence of ravens which are identified by positive integers, so first raven, second raven, third raven, and so on. So, and let B of I denote the fact that raven I is black. Okay? And so we see a lengthening sequence of black ravens, and now we have the hypothesis maybe all ravens are black. So for all I, P of I, and intuitively, if this Lie sequence is longer and longer and there are no counterexamples, this should somehow confirm this hypothesis. So what we want is that the probability of for all I b of I given b1 to bn tends to 1 for n to infinity. I mean, we also want it to tend reasonably fast to infinity, but that's a first step. Okay? And of course, I know that real-world problems are much more complicated, but if we fail on this, we will also fail on more complicated problems. Okay? And the problem is that at least all systems I know of, except for Solomonov, fail on this system. Okay? So for instance, Bayes and Laplace rule and Carnap's confirmation theory, they can't confirm universal hypothesis. They correctly or reasonably predict the next observation of what is the probability the next raven is black, and you get a reasonable answer, or at least not obviously unreasonable. But if you ask what is the probability that all ravens are black, it says 0. Okay? I'll come back to that, why this is really, really bad. Okay? And Solomonov induction, if you've heard about that, that can deal with such sequences, but it is not a probability over logical expressions, but just over bit sequences. And so not really unifying probability in logic, what I'm after here. Okay? I will not really, so we did it in higher order logic because, I mean, in practice you want an expressive logic, and higher order logic is very natural, but here abstract away and sort of you don't have to worry about it too much. And with probability and uncertainty, I guess here that is probably controversial, but I take classical probabilities, Kolmogorov axioms. I mean, that's one way of doing it. I think that's a good way, but okay, if you disagree, that's fine. Okay, but the combination is hard in any case. So the main aim is, given a set of sentences, each having some probability of being true, what probability should be ascribed to other query sentences? The universal hypothesis, or maybe I don't start with any sentences, that's fine. Okay? And an alternative, which I will not consider here, is probability inside sentences. So you could use logic for describing probabilities. So this is probabilities over sentences. Okay, so here's a natural wish list. So the probability should be consistent with your knowledge page. So if you have some knowledge, it should not sort of contradict it. And it should allow for consistent inference procedures, and in particular reduce to deductive logic in the limit that the probabilities are 0 and 1. So probably 1 should correspond to truth or provability, and 0 to falsehood or disprovability. Okay? And so it should allow for inductive reasoning, especially learning the limit of universal hypothesis should work. And so this is my wish list here. And well, you could add another point, it should be practical, but well, it is not yet. Okay, so this wish list, after some while, translated into following technical requirements. First, the probabilities need to satisfy standard probability axioms, including countable additivity. And so even this is controversial for some, but we need something even stronger, and that is Glenn Schaefer called it Cournot's forgotten principle. So that's a principle which is 200, 300 years old, by Cournot obviously, to interpret probabilities, and it is a really nice principle, and in our case crucial principle. And the principle says that zero probability means impossibility. Or whatever is not provably false, you have to assign probability larger than zero. Or you can phrase it sort of with probability 1. Probability 1 in theory means for sure in practice. You cannot prove that because, you relate it to practice, and you may think of a real number and these darts and you throw and you have probably 0 events which appear in practice. But I don't have time to discuss that. To be precise, the event has to be singled out in advance. This solves this problem, so that is a very important principle. Okay? And another one, which is even less known, is the Gaifman condition. So, and we have two equivalent formulations, one semantic one and one syntactic one. One is that logical quantifiers over variables can be replaced by metalogical quantification over terms. What that exactly means, I will show you. These two, this is sort of well known, and these two I will discuss in more detail. Okay? Or more shortly, existence is always witnessed by terms. There is nothing like abstract existence. You may want to argue about it, but if you violate this principle, induction doesn't work, because I will show you these are necessary and sufficient conditions for induction to work. Okay? And the main results is that there's a suitable formalization of all the requirements. I will prove that probabilities that satisfy all our criteria exist. I give one explicit construction in quotation mark of such a probability. I give some general characterizations, well, probably not here, but in the paper. Various examples also in the paper. And, well, the overall conclusion is that I think that is a first step towards a globally consistent unification of probability and logic for learning. And if you don't care about learning, you can use something else, probably. You can still use this, but that's the real point. Okay. I will skip that because I have no time to it. So I show that there exists this distribution. Then usually there exist many such distributions that you have to make a choice. And the maximum entropy principle is a general principle to choose a probability distribution among a set with constraints. We applied it here, but it's rather orthogonal to the main ideas, so I think I can skip that here. Okay. Again, so the choice of logic, I said I will skip over that. The details are surprisingly, although the idea works at least in first order logic and in higher order logic with hanking semantics, it doesn't work automatically for any logic. So there are surprising subtleties. For instance, if in higher order logic I add a description operator, everything seems to break down, which is quite odd, yeah? But that's the case. So we couldn't make it work with description operator. So, but here abstract away from it, just had usual Boolean operators, true and false. Even the abstraction I don't need anymore, I got rid of that here in the slides. T always denotes closed terms. Phi and chi are always sentences with no free variables, and psi of x is a sentence with one free variable. Okay, and then the standard universal hypothesis is for all x pi of x. You can have multiple variables. That's of course you can subsume that. Okay, so first I show how to construct probability over sentences, and these are the standard rules you want them to satisfy. So if phi is valid, so if phi is sort of true in all models, you want mu of phi to be 1, and if you have two mutually exclusive sentences, then you have the usual additivity rule, and conditional probability is just defined like that. That is completely, in philosophy you always have probabilities over logical sentences, while Kolmogorov axioms are usually over events, but you can translate back and forth easily to this level here. Okay, I more or less said that. And here is no countable additivity, because in standard logic you don't have limits. So if we had infinitary logic where you can have infinitely many ends, then we would or could ask for something like counter additivity, but we have that here yet. We have something like the all quantifier, which looks like an infinite end, but that is somewhat different, but not completely different, and I come to that. Okay, that's more or less the Gaifman condition, which is very close to counter additivity. Okay, and then you have probabilities over interpretations. I mean, many interpretations they form a sigma algebra. So if you have a sentence phi, you can ask for all the interpretations which make phi true, so for all four models of phi, and I denote all models by I, and these models, yeah, they form a sigma algebra, and therefore I can define some probability over it. It is completely standard. So the probabilities over interpretations are always with start, blah blah blah, usual rules, mu of star of empty is 0, of I is 1, and then I demand countable additivity here, because here I can do that. I mean, countable unions I can do. So now I want to relate these two notions. So on the one side we have probability over sentences, and on the other side we have a measure theoretic probability over interpretations, and you can go from probabilities over sentences to interpretations by just say the probability of a set of interpretations is the same as the syntactic probability over sentences. I mean, it's also very natural, but to prove that mu star is really a proper probability, that it's a non-countably additive or possibly non-countable, that is trivial. But to prove that you get countable additivity is non-trivial. So first, you need to exploit compactness, and you only have compactness in higher order logic if you use Henking interpretations, or you use first order logic with the standard interpretation of natural numbers. And then you need Theodoris' unique extension theorem. And it is somewhat surprising because on the probabilities over sentences, we didn't even talk about countable additivity, and now we get it automatically. And the reason more or less is that it's not even possible sort of to violate it, because you cannot have an infinite end. The other way around, from probabilities over models to sentences, you do just the reverse, right? And the proof is trivial that this gives a probability distribution. Okay? So the only tricky thing here is in the identifications, the countable additivity, but everything else is pretty standard. Okay. So next, I need to narrow down the number of interpretations, because there are some which are annoying. So let's consider the black raven example again. So we have first raven is black, second raven is black, and so on. And if I take really first raven, second raven, third raven, and all of them, 1, 2, 3, all the natural numbers, then of course this should imply that all ravens are black. But unfortunately, I can't prove that, because there is a non-standard model of the natural numbers where there are more than just 1, 2, 3, 4, 5, namely the non-standard numbers. So this one is not a logical implication of this one. Okay? And therefore it can also be hardly an inductive implication if you don't do something about this interpretations we don't really want. I mean, if you think about counting ravens 1, 2, 3, I think very few of you want to give a raven a non-standard number as an index or something like that, right? Okay? So we need to somehow exclude these unwanted interpretations, and not just for this example, but in general. And the general notion is, rather than 1, 2, 3, is all terms. I mean, what is 1, 2, 3? I mean, in Peano arithmetic is 0, successor of 0, and so on. And these are all terms. So what we need is that so I call an interpretation separating, so the interpretations I want, if all formulas psi of x, the following holds. If I is a model of exists x psi of x, then you can find a closed term such that I is a model of psi where you replace x by t. So that means if this sentence, which contains an existence operator, has a model, of course, in the model there's a domain element which satisfies this, but there's also a syntactic term expression for this. So there's always a witness for an existence operator. Okay, and here that means there are no non-standard numbers, because the non-standard numbers, they don't have witnesses, they're just abstract, yeah? Okay, and I want to exclude them, and I call those interpretations which satisfy this condition separating. Okay, and then you can do the same thing. From a sentence you can construct a set of separating models of this sentence. You have a sub-sigma algebra, and they are measurable. You can assign probabilities over it. It's the same as before. Okay. So effectively, you can avoid non-separate interpretations by requiring the probability of them to be 0. So rather than saying I don't want these interpretations, I just set the probability to 0. Okay? And then you get a syntactic definition which doesn't talk about models, and that's the Gaifman condition. So if we take this formula with one free variable and we replace it by some term t1, and then by t2, t3, t4, think about the natural numbers. We have psi of 1 here, psi of 2, psi of 3. We run through all the natural numbers. We cannot take the infinite and, that doesn't exist in our logic, but we can take the finite and we take the probability over it. And now we can take the limit outside. That's not a problem. And that if the limit were inside and it would make sense, then this one would look like for all x psi of x, right? We can't do that, but we can demand this equation. So we can demand that the probability of a finite and, if we take the limit outside, is the same as the probability of the all quantified. And that's the Gaifman condition. And so informally, that means logical quantifiers over variables can be replaced by meta-logical sort of quantification over terms. So the quantification is just here in the end. And what you can show is that probability distribution mu is Gaifman, so satisfies this condition if and only if the probability assigned to non-separating models is 0, which is exactly what we wanted. Okay, so far so good. The problem is the induction still will not work. Okay, so now let's look at this expression. If I start with mu of for all ib of I equals 0, why not? The Gaifman condition doesn't prevent that. Then the posterior will also be 0. That's a standard result in Bayesian theory. If the prior is 0, the posterior is also 0. So that is not really good, and that's the infamous 0 prior problem in philosophy in induction. And if you look at, say, Laplace rule, Bayes rule, Carnot's confirmation theory, and all systems I know of, and that's quite some, if you ask them, it's mostly those who assign probabilities over propositional sentences and then somehow expand it to predicate sentences. They all get this wrong. They all have the probability of the all quantified sentence to be 0. And the reason why that happens naturally is, so if you look at mu of b1 up to bn, yeah, it is very natural that you have an IID problem, or even if it's not exactly IID, it's somewhat IID-ish. So if it were IID, and you have some, say mu of b1 would be some p, then you would have here sort of p times p times p, and the product of all p's larger than 1 would converge to 0. And this left-hand side is bounded by the right-hand side, and the right-hand side tends to 0, then the left-hand side is exactly 0. So it's very natural if you assign probabilities over propositional sentences, then that the probability over quantified sentences will be 0. That's, if you are not super careful, this will happen. I tried to be super careful and this still didn't work, so I needed to directly define the probabilities over the quantified sentences. Okay. And how do we do that? Well, I just demand that it's larger than 0. I can do that, right? Okay. But of course only for all sentences for which it is possible. So for instance, for a contradiction, I cannot demand that it's larger than 0. So only for the reasonable sentences, and I have to tell you what reasonable is. Okay? And this gets me to the Cournot condition, because Cournot said that, so from the positive side here, all sensible probabilities should be non-zero, yeah? Or reversely, probability 0 means impossibility, or probability 1 means certainty, which is sometimes called non-dogmatic. I mean, if you set a probability to 0, although you could set it to non-zero, then you're very dogmatic. You say, I'm sure this will not happen, although you don't have the evidence for it. Okay? And the Cournot condition is that all phi which have a separating model should have probability larger than 0. If I would just say all phi which have some model, I would have got a contradiction to the Gaifman condition. So I need to restrict it to the separating models. Okay? Okay, so far so good. So let's now look at the black raven again. And let's assume we have a mu which is Gaifman and Cournot. So we look at this expression here. The first thing we can write it as, the conditional probability is of this and this, but this is subsumed by this, so this is just the probability of this, divided by the probability of this. That is just standard definition. Next is, we take the limit n to infinity, where the denominator goes to mu, this one here. And this uses the Gaifman condition, because we said Gaifman means that this limit converges to the quantified mu. And then by Cournot, numerator and denominator are non-zero. That's of course important. If there were 0 divided by 0, I wouldn't know what to do, but by assumption by Cournot, this is non-zero and I get 1. So that means asymptotically, if I start with any mu which is Gaifman and Cournot, I can confirm this universal hypothesis. So which is very great. Finally, it works at least on the black ravens. And you can show a general theorem which says that you can confirm all universal hypotheses, so all hypotheses which have an all quantifier, that have a separating model, and all the others are sort of contradicted anyway, if and only if mu is Gaifman and Cournot, which is very nice, it's sufficient and necessary. But I haven't shown you that such distributions exist, right? Well, I want them to be Gaifman and Cournot, but maybe that is not possible. And indeed, that is sort of, well, many parts were tricky, but that is also not so easy. So the simplest construction is the following here. That is maybe not the most useful one. You enumerate all sentences which have a separating model. Of course, you cannot do that constructively, but abstractly you can do that. And for each sentence, by definition, it has a separate interpretation, and you choose such a separate interpretation, and you add a probability mass of 1 divided by I times I plus 1 to this interpretation. You put this probability mass, point mass, to this interpretation. And the reason for this is if you sum that over all I, this gives 1. You could also use 2 to the minus I, which is worse. But theoretically it works. And now, I have a probability distribution over interpretations. So it's 0 for all interpretations except for this countably many where it has a point mass. And then I can use my previous theorem and get back to probabilities over sentences. Okay? And what you can prove is that the mu I constructed here is Gaifman and Cournot. Of course, that is a very specific construction, right? I mean, you have some choice here in the order, and this you could choose differently, but you don't get all of the distributions. So one reviewer pointed out you can't get the uniform distribution, IID distribution, which is very important, and that's indeed true. I mean, even with the general characterization, you can't get that, but you can get asymptotically uniform distributions, and there's good reasons why you don't want a strictly uniform distribution a priori. Because if you have an IID distribution a priori, and your data is not IID, you cannot learn anymore, right? You want to mix between, say, the IID and some distribution, which is Gaifman and Cournot, which learns. And if my work is IID, this will die out and the uniform will survive, and if it's not IID, then at least you have a chance to learn. Okay? So I will skip the part where we have some prior knowledge, how to get distributions which are consistent with your prior knowledge, and then how to get the minimal informative distribution which has minimal entropy given the knowledge constraints. What you can show is you have, the generic definition of KL divergence between two distributions is just this one here. But look, the space of interpretations is a very, very abstract space. But luckily, measure theory has been developed for abstract spaces, so that is not a problem. But it is very hard to deal with this. But you can write down and you can prove that this purely syntactic definition is equivalent to this semantic definition. And this is indeed, in a sense, finite. So you take finitely many sentences and their negation and end them, which build a basis, and then you compute the entropy, and then you take the limit n to infinity. You still have to take the limit here, but this is a much more benign object than this one. I mean, this can be sort of approximated by real algorithms. Okay, and the theorem is empirical. Okay, so here's an example. What happens, I mean, as usual with maximum entropy, if you have probability constraints rather than expected constraints, they're more or less rescaling the original probability distributions. Okay. What I have not talked about is alternative tree constructions and general characterizations of probabilities that satisfy some or all of our criteria. We don't have yet a completely satisfactory, complete characterizations of all distributions which are Gaifman and Cournot. We have a satisfactory characterization of all distributions which are Cournot, and some characterizations of those which are Cournot and Gaifman, but they're still open problems, and it's not so clear whether you can even solve that in a nice way or only in an ugly way by going through the infinite list of sentence or something. Because this construction was actually quite nice, and we also have some not so nice constructions. Okay? Well, there's much left for future generations. So I mentioned briefly Solomonov induction, and this feature didn't feature at all in this work, but it was strongly motivated by it. And actually, in the workshop version of the paper, I mentioned briefly how to combine that, but I mean, this has not really been worked out. I mentioned that the description operator causes us deep troubles, which should not be the case. Of course, ultimately, everyone wants to use these things in practice, so we have to develop practical approximation schemes. So Gaifman already in the 70s, I mean, this was a fantastic, no, 80s, it was 82. I mean, this is a fantastic paper. I mean, he came up with the Gaifman condition. But it was mainly a very negative paper. You cannot do this, you cannot do that. So, I mean, it's very hard to approximate that, and you have to make severe concessions. But, I mean, that's life, right? I mean, in practice, things become messy, and you have to do whatever you can do. And it's not really impossible. For instance, you can show that if you only want to confirm sigma, so pi 1 sentences, and you can construct a pi 2 probability which is able to do that. Which is, I mean, this is still not computable, but not too far up in the arithmetic hierarchy. While these Gaifman and Cournot distributions I constructed are even outside the arithmetic hierarchy. So, I mean, it can't get much worse. Well, here are some other contributions, but I guess you can read them in the paper. So, this is the long version of the paper. Then you have, of course, I think the workshop version is much nicer to read, yeah, because it drops all the technicalities. This is a great paper, but also very technical. I mean, our paper was heavily inspired by that. Farmer's paper advocates higher order logic. I'm not convinced, but that's sort of the most convincing paper if you want to convince somebody about higher order logic. It's really very nicely written. That's a paper which combines probabilities inside and outside sentences. And if you care about the induction problem in general, but not with respect to logical expressions, but just sequences, then this is, I think, quite nice to read. Okay, thank you for your attention.
Any questions?
I just have one question. I know you avoided this to the start, but if you insisted on the interpretation being a standard interpretation, which is to say that the domain is always, say, the natural numbers,
Yeah.
do you get exactly the Gaifman and the Cournot condition?
Yes.
Exactly. So there are two.
Yeah. I mean, if you're only dealing, let's say, with Riemann axioms, you get exactly the Gaifman condition by limiting to the standard model of natural numbers. If you have more richer domains, then of course you need, other terms. I mean, if you have rational numbers, you have something else. But in the case of natural,
your construction of picking out this mu is based on essentially going over sentences and picking out this model, which is standard.
picking out what?
The standard interpretation.
Yes. Yeah.
To get this, to get rid of these non-standard models.
Yeah.
Basically, what you were asking is that the for all and existential quantifiers are witnessed.
Yes, right.
And this can be achieved by introducing a couple of axioms for that?
No.
No?
No. If that were the case, we could define, say, natural numbers axiomatically, right, uniquely, which is impossible.
Yeah.
by Gödel, unfortunately. It has strong relations, I realized later, with this omega, one second. So there is something called omega consistency, or truth value interpretation, or so it's a non-tasky way of interpreting quantifiers, and there are many systems which seem to go in these directions under different names, but it's not sort of the classical way of interpreting logic, but it's a way which people in the past and philosophers still sort of deal with, which is sort of quite interesting. What you want to add something?
No, I mean, even if you restrict to first order logic,
yeah,
it's not, I mean, because for instance,
even first order logic, it doesn't work, right? Because we cannot substitutional interpretation of quantifiers. That's more or less, or possibly exactly the Gaifman condition if you have probabilities or the separating interpretations. So now look, we cannot categorically axiomatize the natural numbers.
No, yes, this is for sure.
Yeah.
But just to enforce witnessing of the quantifiers.
Now, if we would enforce that, we would have a categorical interpretation.
Yeah.
Because if we enforce witnesses, there's only one interpretation of piano.
Yes, okay.
Yeah.
No, I was thinking only on, let's say, predicate couples, not. Okay.
Other predicate in general.
Perhaps we can discuss.
There's one thing which maybe you could have asked. Well, but in higher order logic, we can categorically. But this is related to the standard interpretation and not the Henking. And whether I use the Henking which we do or the standard, we all run into problems. Okay, but you want to continue with the next slide.
Okay, so we have